So, good fanboys there. So, so how many of you have heard about free monads or know what they are? Okay, so good amount. How about kleislis arrows? All right. So the talk is about patterns that you usually find in functional programming, things that you can actually use to architect your application, but also some utilities that come very handy when you have to deal with certain type of scenarios in your application. And the purpose is to show how you can actually go purely functional. Examples are in Scala, though the concepts are applicable in any language that supports functional programming. So I want you guys to go ahead and interrupt me at any time. I'll be happy to answer any questions that I know. And let's get started. How many of you are familiar with Scala or have used Scala before? All right. Hopefully it's a good amount. Okay. So first of all, a few acknowledgements. This is nothing new. There's a few papers out there. There's a few talks that cover similar concepts. I organize them in a slightly different way. But here's a few of them. Scala set is a library for functional programming in Scala. Scala is a hybrid language. For those of you that don't know Scala, it's not a functional language. Then we have Runar, which is the creator of functional programming in Scala, the Red Book, known as that. They show you how to actually do purely functional types. Noel Markham, he has a similar talk where he explains free monads. If you guys Google this up, I'll get some links later. And then also, there's a paper called Data Types a la carte by Wouter Sierstra, if I pronounce that well. But basically, they show you how you can combine free monads and their algebras and with code products to actually compose them. Contrary to what many people say, monads are not composable. Well, depends on what kind of monads too, right? And then Raptor, finally, by John Perry. We are going to see a couple of the types that I use every day with Raptor and why they are important to develop them. So first of all, functional are first classes in functional programming architecture. So everything we do, most of the time, what you guys do in OOP, who works with OOP languages doing Java or, okay. So every time you see a pattern, it's probably something you can solve with functional programming. Like when you see dependency injections, there's many ways to solve it with functional programming. That is not necessarily runtime dependency injection with Spring or Dagger or whatever. We're going to see a few of those. And most functional patterns, of course, are derived from category theory, so I'm going to make some assumptions that you guys understand some of the concepts. If you don't, that's fine. You can interrupt me. I'll try to explain it. It's going to be kind of like, we don't have much time. I know you guys are hungry, so I'm going to try to cover as much as I can, but not get too caught up on the details. And when I build an app, this is like the main building blocks that I want from my architecture. For once, I want it to be completely free of interpretation. What does that mean? I want my program to be defined here, and I want the runtime expression of the program here. I don't want to mix any details of the framework or the actual runtime with the business logic that is going to compose my program. We also want it to be composable pieces. So if I have an application that has persistence and has user input, I want to be able to combine them in such a way that produces something useful. I want dependency injection because I don't want to instantiate all the types and because I want to be able to then later test my components without actually depending on the whole context, right? And I want it to be fault tolerant. That means if there is an exception, if there is a failure, we should be able to recover from it. And not just like catching throwable. We should be able to catch the specific exceptions that happen in our application. And this is how we're going to solve the pieces, right? So we're going to talk about free monads, how they give us the power of decoupling the interpretation of our software from the actual definition of it. We're going to talk about code products, which is what we use to actually combine those free monads, those algebras of our application. We're going to see that there is a few techniques in Scala, which are also some of them applicable to other languages, that are not the cake pattern or the runtime wiring of dependencies. And we're actually going to talk a little bit about dependently typed check exceptions. And the last part is very similar to what John Perry was doing today in the keynote. We're going to use phantom types to keep track of exception signatures. So what is a free monad? Does anyone know what a free monad is? And care to explain it to everyone? For the purpose of this talk, it's a lot of things more than this, but it's just something that when you have a custom algebra, so think about a data type that has a sealed trait, or whatever it's in your language, and then multiple types of it, then that's your algebra. So if you have a persistent algebra, you may have operations such as get all, or put, or add, right? And then the advantage of free monads is that when you use them, your program becomes like a big tree with all of the computations, but they haven't been interpreted yet. So you can fold that tree over an interpreter, which we're going to see how it looks like. By the way, this presentation is running Replacent, which is a tool by Marconi Lana. It's one of a coworker of mine. And he uses SBT, which is the Scala build tool, and allows you to run interactively all the code as you go through the presentation. So I'll give you at the end a link. You can download and run it and play with it. So what is an application? We said that a free monad, it's an algebra that it's free of interpretation. So an application is nothing but the coproduct of having all those algebras interact with each other. Does that make any sense? We'll see. It's more easier looking at it than actually reading definitions. So we're going to build an app as we go. Code is going to be there already, but we're going to run it, see that it works. And we're going to start with our model. Sometimes when we write apps, what do we do first? We just go and write our model because we understand what are the key pieces that we need to actually use in our application. So we have a contact. Let's run it. There it is. It's in scope. And then here's our first algebra. Here's our first chunk of usage of the free monads. So our application has to interact with the user. And there's two things that it can do. One is ask, giving a prompt, and then receive a value back, which in this case is going to be of type string. And then the other one is simply tell the user something. So similar to what println does, performing a side effect and forgetting about it, no value back, or unit in this case. Any questions so far? All right. First algebra defined. Let's go next one. So what can our application also do? Our application can actually take and save stuff. In this case, we were talking about contact. Contact is our model. So we can add a contact, and we can get the list of all contacts. Run it. Next. So we said earlier, an application, it's nothing but the coproduct of the algebras that we have defined and how they interact with each other. So that's right there, right? We have a type. That's going to be our whole application on its own. And then on the right side, there is our two algebras. Now you may think, like, what happens if I have more than two algebras, right? My application is probably more complex than this. Well, it happens that if you keep like nesting code products with other code products, you end up with the same result. For simplicity, we are just using two here. So this is more of an implementation detail. I'm going to explain it a little bit. It turns out that when you use free monads and you have an algebraic data type, you don't need to implement map or flat map or all the functor instances or all the stuff for yourself, because there's a concept called couneta, or the uneta lemma, inside the free monads. And the next version of a Scala set, I believe, they do automatically for you, so you don't have to do this piece here. But basically, that gives you a monad instance, or it's going to help you get a monad instance for free for all of your algebras. That means that you're going to be able to use your algebra directly on a for comprehension or anywhere where monadic context is used. So in that paper, Data Types a la carte, they kind of show you how you can actually combine monads. And it turns out that you can actually combine in this way. There's an inject type class. I'm not going to go into detail here, but it basically allows you to lift any algebra to the coproduct space so that you can actually use the coproduct as if it was like the monad that combines both, in this case, interact and persistence. Oops, this is kind of messed up.
Raul, one question.
Sure.
If you are, let's say, having this composition,
Mm-hmm.
with monads, we are, let's say, able to control at runtime, so to access some context information.
Yes.
This context information, so it's available all the chain. So for all these process,
Mm-hmm.
still can say, okay, I can have whatever context and process it and provide feed this context. Is that?
Yes.
It's that in that piece of block that's possible.
Yeah. So basically, it's like, what are monads useful for anyway, right? So they're useful for binding to computations and obtaining a value which may have not been computed yet, but then you can perform operations. So if you think about option and then you have a chain of flat maps, you can keep performing operations on the potential value that the option is fulfilled. So it's future or any other types. So yes, you can access the context, and then you can do the same with free monads. We're actually gonna see an example of that in a second. So here what we're doing is basically oops, sorry. So we have tell and ask, that was our algebra, right? But we want to be able to obtain the monadic value right away. We just don't want a value of ask and tell. So what we do is like we have this class that encapsulates the operations, and it's just basically a delegation pattern. And what it uses the lift function that we defined before. So it can lift any value, such as ask and tell, that's an algebra, to the free monad of a functor, or a type constructor, sorry, f, which is going to be your application. So that gives us the flexibility that we can use those classes outside of the context of the coproduct of the application if we wanted to mix and match them in some other way. Like we can have several layers like persistence, views, controllers, whatever you name it. And then each one of those layers, have its own, be its own like application in a way, and then combine them all together in a super application that has all the coproducts. Sorry. Anyway, so we have this application, and here we're actually using a technique in Scala. We are using implicits. We're going to do the dependency injection. Why? Because interact, which is a companion object to that class, any implicits defined in the companion object, they're always accessible to the scope when someone needs it. So if you require an implicit of interact, and that immediately you will get this one. And that gives you the runtime instance, or the instantiation of what we need to operate. And we're going to do exactly the same for data source. So we said we had two operations, right? Add contact and get all contacts. So we are lifting, again, using our function from before to lift it to the coproduct. And that's going to give us the two operations we need. And we have the same implicit to cover dependency injection. So here's our program. So now we have a program, right, with our two algebras. This is how you will combine them. We're using here a for expression, which is similar to what we just saw on the talk before. That's just like the Scala version of it. So what this is doing basically is every time you see an error here, so in a for comprehension or in a monadic context, you always end up with the same monad that you started with. So if you're starting, in this case, with ask, why can't we combine ask and add contact if monads do not compose, if they don't combine? It's because they're lifted to the coproduct of the application. And with the inject type class, we're able to lift them that way. So we're saying, hey, I'm going to ask for a first name. We have a monadic binding here, so this is similar to if we were doing like flat map, right? This actually translates into a chain of flat maps and map and so on. So we have first name, last name, phone number, and then we're going to perform a side effect. In Haskell or other languages, you probably use IO or some similar monad here, because Scala is just like dirty, just lets you do it in line. So we're going to perform that side effect right there, creating a contact. We're going to actually get ask persistence. So now that I've added one, give me all of them. And I'm going to print them out. I'm going to tell this, so here's your contacts. And because this program doesn't really do, it's actually the top level application, so it's just going to yield unit because there's nothing else. It's the effect. It's the final effect on top of the chain, right? So if you've noticed, we actually wrote a program, a bunch of business logic. There's no println statements. There's no console read line or any of the actual APIs that you use to actually do the real work. Sorry about that. So how is that possible? That's possible because when we yield unit, we're actually going to end up with like a tree-like structure of free monads. It's just a description of our program. It's not the actual real final computation. It's just a description of our business logic. If I wanted, I could implement ask in terms of something asynchronous. I could go out to the network in an asynchronous way with a callback, then continue the process. So my actual business logic is not contaminated by the semantics of whether things are synchronous or asynchronous, or whether things are reading from the command line, or if it's maybe it's an Android application. Maybe it's running some UI and asking for some values and computing them. By the way, the import IND is just a shortcut to use ask and add contact without the fully qualified name. And if you guys notice, the interacts is now parameterized to the agenda app, which was the F in the definition. So we're actually using agenda, the coproduct, as the type constructor that is going to parameterize everything. So this is how you actually write the runtime of your program. So because this application, I wanted to implement it with the console, my interaction algebra, so interact, is actually implemented using console semantics or APIs. So for each one of the elements in your algebra, you tell it how it's going to work. There's something interesting here, this interact to ID and ID. Who knows what a functor is or map? So basically, this is called a natural transformation. And you can think of it as like a, probably it's not the right word, but it's kind of like a type level. It maps over the type constructors and not the actual values. So you say, I want to turn an interact into the ID monad. What's the ID monad? Just the entity, so the value itself. If we were in the context of maybe asynchronous work, we would use task or future or any of the other monads that allows us to do things in an async way. And then for the data source algebra, data up, we are just going to use an in-memory list. Scala lets us do mutable stuff, so for simplicity of the implementation, we didn't do like a state monad or any other more complex things. But in this example, this is just an in-memory list. When we add a contact, we add it to the list. Return unit, which was the return type. If we ask for all contacts, we just like get back the list of contacts. So we had two problems here. We have two different interpreters, but our program is of type agenda app, right? So this is another kind of like way. It's more complex, and I don't expect you to understand what it's doing. But basically what it does is like, if you give me two interpreters, for example, the console one that we just wrote, and then data source one that we just wrote, whenever I'm evaluating the free monad hierarchy or a call chain, if I'm talking about interaction, meaning I'm on this left side, I'm going to run this interpreter. If not, I'm going to run this other one. So basically, it's just branching to run an interpreter or another. And now we can say that our application can be run having the in-memory data store interpreter and the console contact reader. And the thing at the bottom is another implementation detail of the code unit. We have to lift them up because the free monads that we just composed or we just like created are in that context. So we have a program that is a description. It's free of interpretation. It just describes our business logic, right? And then we have a bunch of interpreters that we have like put into one single object, then can know which one to run when we run our program. So free monads in Scala set are implemented also using trampolines. It's not expect you to know what that is, but if you're interested, it's pretty cool. Basically allows you to run computations without blowing the stack. So you can like jump, take the whole tree of computations before it's evaluated and move it over to another thread or another way to not blow the whole method stack. And once we have this, we can just run our program, separate from its interpretation. And unfortunately, you're not going to see what I'm typing here, because there's a bug in represent. So remember our program before that have ask first name, ask last name, ask phone. So it's performing all the computations after I folded it through the interpreter. So I type a bunch of stuff here, but you get the picture, right? So we have now the final value. We actually have still our program, which still is in the context of free, and our program can be completely reused. So it means that we can rerun it with different interpreters all the time. What does that mean? That if you have certain types for production that are different from the ones from testing, you can just fold over ID for testing, and you don't have to bring in the whole context of asynchronous workers and thread pools and so on. Right? So basically, we've seen how we can actually compose monads in a way that is reasonable. We just have to use the right type of monads. Not all monads compose. When they don't compose, what you have to do is monad transformers. We're not going to cover this on this talk because there's a better talk than this one. For that, I think Lars is called Optimus Prime T. I think you guys should go to that if you're interested in how you can combine monads with transformers. And we're going to talk about a few other types and a few alternatives of what we just did. So we use implicits for dependency injection, but we can also use kleislis arrows. A kleislis arrow is just like a function. So given an input, in this case A, it's going to return like a type constructor with a value. So that value could be like list, option, either, future, you name it. So when that function has that shape, it can be considered a kleislis, and Scala set provides a facility that you can wrap those functions into kleislis object, and you can perform a lot of cool things. One of the cool things that kleislis has is that they're monadic. That means that your functions can be monadically sequenced over for comprehensions in the same way we did with free monads. So given this, right? So we have a function that takes a string, returns an option of an integer plus 1, and then another one that does the same thing. If we run them, what do we get? another function that hasn't been applied yet. So if you notice the x string, we can defer the input parameter at any point in our program. We don't have to apply the function right there. We can compose and compute on the bound variables a, b, any way we want. And the only thing we have to do is provide the actual input parameter down the road. And this is called dependency injection. There is no need for frameworks. There is no need for anything else. You can use kleislis arrows or implicits in Scala. So we have talked about being free of interpretation, having composable pieces, having dependency injection, and we're going to talk a little bit about exceptions now, because that's something very important in everyone's application, at least on mine. So can anyone tell me what's wrong with this? Maybe if I run it, you guys can get a hint. Anyone? All right. First case, we're using a Scala features. It's just an example of a type that, for simplicity, the API designers decided they're just not going to care about the type information of the exception. So your type system doesn't help you, even though we fail with a number format exception. F contains a feature of nothing. There's no way to reason about that except for recovering and shooting in the air and hoping that it will catch it. So you need to know what the exception types are. Most types don't do that. Let's see another one, try, which is one of the most commonly used ones. Try monad. We are throwing a number from an exception. Try is lazy, so that block executes down the road, doesn't blow the stack right away. And what do we get? Try of nothing. Not useful at all either. We have to again recover and then say case whatever and provide a type signature that actually hopefully will match the actual runtime value, and then we can recover from it. But we don't know the actual type. Take Scala set disjunction or any of the disjunction ones. We have here a runtime exception, but we have a problem with that, because if you guys look at the definition of A and B, first, I had a number format exception, then a runtime exception. And ideally, I will know that the number format exception is still there, because that's probably the cause of it in some cases, right? Yet, we got a runtime exception. Why? Because when you have different types, they kind of coalesce to the most common supertype, so you end up with a runtime exception. In most cases, you end up with a throwable, which can be anything, like really anything that the virtual machine can throw. You end up with that, and then you'll have to look at the code, see how it's implemented, and see what potential exceptions may have been thrown. So we don't have to settle for throwable. There's a few techniques we could use. We could use nested disjunctions like the one we just saw, but keep on accumulating on the left side, on the exception side. That's kind of a pain to deal with because of the complexity of having multiple disjunctions. But then we can also use the limited monadic dependently type accumulating checked exceptions. And I haven't really came up with this name. That's actually John Perry, so if you have a problem with it, he's right there. And how does that work? So I'm going to show you guys a type that we commonly use at 47 degrees for handling errors and results and stuff. It comes from the Raptor library by John Perry as well. And result has something very cool, which is it has 3 possible outcomes. The first outcome is an answer, which is like the positive value saying everything is okay, here is your value, this is your computation, this is what you have. The next one is the errata, which it's this made of ended with a potential exception, which is of this type, right? And the other is unforeseen, which is we are in a non-pure world in Java, so we are interoperating with libraries that are potentially throwing exceptions that we are not even aware of. So this safely captures those, places them on a throwable, which we can recover from. And how cool is this? For those that like exceptions. Anyway. So in the first case, we were capturing a number format exception, right? And in the second case, we have an illegal argument exception. So should we have used this junction of any of the other types that kind of have like a single type on the side, we will end up with like a runtime exception. Or illegal argument, because I believe number format is actually illegal argument as well. But instead, what we get in the type signature, number format exception with illegal argument exception. So we have the type information to recover from. If we wanted to, we could recover from this right now. Sorry. So we have all of the exceptions, or type op, it's going to have those. So we know that if we wanted to recover to an actual value of answer, so if we were computing ints in this case, we can capture each one of those cases and actually turn it into an int with whatever logic, right? Or if we pass it down the stack to the next layer in our architecture, the next layer will receive the actual right signature for the exceptions that the previous layer may have thrown. So in this case, returns an answer of 0. And alternatively, like if we don't want to, say, move persistent exceptions over to the model or the view layer, because it may not be even available in the class path, or we don't want them to get mixed up, then we can easily just turn any exception into a custom one, which we use semantically throughout your code. Right? So we looked at free monads. We've learned that they are free of interpretation, that they completely allow you to decouple your application business logic from the actual runtime interpretation of it. We actually saw that we can use code products and then inject type class to combine those monads in the same comprehensions and sequencing through them. We've learned that dependency injection is just not a framework. It can be done with most languages that are functional. And one way to do it is explicitly and implicitly where supported. And actually, to recover from exceptions, we want to keep and preserve all of the type information. So there is ways to do that today, and there's no reason why we have to settle for throwable. What's next? Well, I talked a little bit about this. You need transformers. You should go to Lars talk for sure. There's also an article that I wrote a little bit about transformers and how you can, if you're learning about them, how you can combine things like what happens if I have a future and then the result is an option. I don't want to have like a pyramid of nested flat maps. How can I solve that problem? So that article kind of like goes over that. And if you want to access the slides and the presentation and the source code, they're all available in GitHub and Speaker Deck. So feel free to play with them, submit pull requests, take it and do whatever you want with it. And that's all I have.